All right, let's dive right into this explainer. We're putting you in the driver's seat of a spacecraft for a thrilling journey into the absolute most extreme boundary in the entire universe. Black holes are undeniably some of the most mysterious objects out there in the cosmos. They're invisible, incredibly dense, and they pack gravity so unfathomably strong that literally nothing escapes their grasp. But what would actually happen if you, personally, took the plunge? Well, today, we're going to map out this exact theoretical journey using modern physics. So, to kick things off, would you die instantly, or maybe travel to another universe? Pop culture and sci-fi have definitely given us some pretty wild ideas. I mean, some myths say they act like giant cosmic vacuum cleaners, just sucking up everything in sight. Actually, that's not true at all. They only pull with the gravity of their mass. Other myths claim you'd die the very millisecond you got close, or maybe get zapped through some portal to another dimension. But today, we're relying strictly on Albert Einstein's theory of general relativity to separate fact from fiction. We're going to walk chronologically through the true physics of the fall. Picture this. You're approaching your destination. At first, just looking out the window of your spacecraft, honestly, nothing seems terribly out of the ordinary. You wouldn't see a giant hole floating out in the middle of nowhere. Instead, you'd see a perfectly dark sphere. And the reason it's perfectly dark is because this object is so incredibly dense that it has fundamentally curved space-time right around it. It's not some empty void, it's an immensely compact mass. Now, what's super interesting is what is happening around that sphere of total darkness. You wouldn't just see blackness, you would see this stunning, heavily distorted halo of light. We call this phenomenon gravitational lensing. Because the black hole's gravity is so intense, it actually bends the light from the stars located behind and around it. It acts exactly like a giant cosmic magnifying glass. Those stars would look stretched, curved, and warped into a really mesmerizing, glowing ring. And here's a massive, kind of counterintuitive twist to our journey. Your survival at this point heavily depends on the size of the black hole. Now, you might think a massive black hole is way more dangerous, right? Actually, it's the exact opposite. If you approach a small black hole, the gravitational forces near its edge are incredibly violent, and you'd likely be destroyed before you even get close. But if you approach a supermassive black hole, talking millions or billions of times the mass of our sun, the forces near the edge are much weaker. You'd actually survive way longer on your descent into a supermassive one. So, the absolutely crucial point here is understanding why a small black hole would destroy you so fast. As you get closer, gravity increases dramatically. But here's the kicker. It doesn't increase evenly. It increases across the distance of your own body. Think about it. If you're falling feet first, your feet are slightly closer to the center than your head is. Because of that, gravity pulls significantly harder on your feet than on your head. This difference in pull is exactly what physicists call a tidal force. Which brings us to one of the most terrifying yet totally fascinating predictions of modern physics, spaghettification. And yes, believe it or not, that is the actual scientific term. Because of those extreme tidal forces we just talked about, gravity starts to stretch your body vertically while simultaneously squeezing it from the sides. You'd get longer, thinner, and more stretched out, honestly remarkably like a strand of spaghetti. Eventually, the stretching gets so overpowering that your bones, your muscles, and eventually your very atoms would just be pulled apart. You would absolutely not survive this phase if it hit early. But for the sake of our journey, let's assume you've chosen a supermassive black hole so we can bypass early spaghettification and keep on descending. Okay, moving into section 1, the illusion of time. Let's see Einstein's general relativity in action. The contrast here is just staggering. From your perspective, falling in, everything feels totally fine. You check your watch, it's ticking normally, you feel your heartbeat, it's completely steady, time feels completely ordinary. But to someone watching you through a telescope back on Earth, they are seeing a totally different reality. To them, your clock actually appears to slow down. The closer you get to the edge of the black hole, the slower you appear to move, until you seem almost completely frozen in place, just hovering right there at the boundary. This dramatic time difference brings up a pretty mind-bending question. Could you see the future? Well, because time outside the black hole is passing much faster relative to your time, if you were to look back out into space while falling in, you'd basically see the universe running on fast forward. You might watch distant stars and galaxies evolving, dying, just zooming by. You're practically watching the future of the outside universe unfold. Obviously, you wouldn't get to watch the entire future of the universe forever, though, because your own journey is pulling you toward a very finite destination. And that destination begins at the event horizon. You've probably heard this called the point of no return. Think of it like standing in a river just upstream from a huge, roaring waterfall. If you're far enough away, you can swim against the current and make it to shore. But once you drift past a certain invisible line in the water, the current becomes absolute. It doesn't matter how hard you swim, you're going over the edge. The event horizon works exactly the same way. Once you cross this invisible boundary, not even light itself is fast enough to swim upstream against the gravity. So, okay, you've crossed the boundary. The universe is fast-forwarding behind you, and you're slipping deeper into the dark sphere. Is there any way out? Can anyone save you? The answer is a chilling, absolute no, because nothing can move faster than light, and light cannot escape the event horizon. No signal can ever leave this place. If you tried to radio for help, your message would literally just fall inward right along with you. No rescue spacecraft could ever reach you and pull you out. Behind you, the view of space would become increasingly, infinitely dark, which, by the way, is exactly why black holes appear completely black to us looking from the outside. To really wrap your head around why escape is totally impossible, consider this wild reality. Inside the event horizon, space and time themselves are curved so intensely that moving toward the singularity becomes unavoidable. It's not just that gravity is acting like a super strong magnet pulling you back, it's that the actual geometry of space and time is bent. Even if you fired up the most powerful rocket engines ever built and pointed them directly away from the center, you wouldn't move outward. Inside the event horizon, all paths literally point inward. Falling toward the center becomes as mathematically unavoidable as moving into tomorrow. Now, before we hit the very bottom of this cosmic well, we've got to do a quick reality check on a favorite sci-fi trope. Could this unavoidable path lead you through a wormhole into another universe? I know some mathematical solutions to Einstein's equations do suggest the idea of wormholes, hypothetical tunnels connecting distant parts of space and time. But we have to stick to the hard facts here. There is absolutely zero physical evidence that real black holes contain these portals. Theoretical physics tells us most wormholes would collapse almost instantly, and frankly, we've never actually observed one. So, grounding our explainer back in proven science, no, you aren't going to another dimension. You are going straight to the center. Which brings us to Section 2, the ultimate mystery, reaching the center. All right, we have finally arrived at the singularity. This is believed to be an incredibly tiny point at the very center that contains literally all of the black hole's mass. Current theories tell us that this point has infinite density and infinite curvature of spacetime. But I'll let you in on a little secret about physics. Whenever physicists start getting infinities popping up in their math, it usually doesn't mean something is actually infinite. It's a massive red flag. It indicates that our current theories are simply incomplete, and the math has basically broken down. Because our current math completely breaks down at the singularity, nobody knows for sure what happens here. Figuring it out requires scientists to merge the physics of the very large, gravity, with the physics of the very small, quantum mechanics. And, spoiler alert, we haven't successfully done that yet. But the possibilities are so fascinating. Maybe space and time simply end completely at this dot. Maybe matter gets crushed into some entirely unknown, bizarre quantum state. Or maybe entirely new, undiscovered laws of physics take over completely. Whatever it is, if you reach the singularity, you and everything that made you would just become part of this ultimate mystery. Let's take a breath and recap this incredible cosmic journey we just took, because it really proves just how wildly the laws of physics completely transform in the universe's extremes. First, you approached the dark sphere and witnessed gravitational lensing warping the starlight. Second, depending on the black hole's size, you faced the fatal stretching of spaghettification. Third, you experienced time dilation, watching the universe fast forward while you appeared frozen to Earth. Fourth, you crossed the absolute point of no return, the event horizon, where all paths just bend inward. And finally, you arrived at the singularity, the place where our current understanding of reality simply ends. But I want to leave you with one final provocative thought. Back in 1974, the legendary physicist Stephen Hawking proposed that black holes don't just sit there forever. They actually slowly leak energy through a quantum effect called Hawking radiation. Over unimaginably long timescales, way longer than the current age of the universe, a black hole will gradually lose mass, shrink, and eventually evaporate completely. So, if the black hole eventually disappears, what happens to the matter, the spacecraft, the information that fell inside? Does it evaporate back into the universe, or is it just gone forever? It remains one of the most hotly debated questions in modern physics today, leaving us absolutely mesmerized by the greatest mysteries of our cosmos.